something. And the question is, how can someone prove that it knows something, okay? How can I prove to you that I know something? And the notion that is used here is that a machine knows something if giving access to that machine, we can efficiently compute that thing, okay? So we don't like open the machine and find that, like, you know, in some memory location it has knowledge of this witness. What we do show is that if we have access to the machine, then we can interact with it, and using this interaction, we can learn the witness. So this is the notion of proof of knowledge. So the proof of knowledge basically says that there's, that there exists an extractor, some algorithm, that obtains from the prover P a witness, such that the witness is with X, satisfies the relation with X. So essentially, the extractor interacts with P and can obtain the witness with essentially the same probability that the prover P is able to convince us that the proof is correct. So if the prover always convinces the proof is correct, then we can always extract the input. If it convinces with some probability P, then we should also extract this witness with probability P. Okay. Now, zero knowledge is an amazing concept, and it's used for can be used for many things. And it's also being used in many applications in cryptography. For instance, I work a lot on MPC, on secure computation. And in MPC, it's easy to design protocols that are secure against semi-honest adversaries, meaning adversaries that somehow run the protocol as it is defined. And the problem is that we define protocols that are good against adversaries that kind of follow the rules and don't try to break the rules. And then in real life, we would like the protocol to run against, you know, any adversaries that doesn't necessarily follow the rules. So for this, we can use zero knowledge, as was suggested by a paper by Goldreich, Mikali, and Vigdezon. Is it Goldwasser, Mikali, Vigdezon? Goldreich, Mikali, Vigdezon. And this is the GMW compiler. Basically, they say, okay, each participant proves in zero knowledge that it followed the protocol. So we design a protocol that is only good if the parties follow the protocol. And then the parties run that protocol and also prove to us in zero knowledge that they indeed follow the protocol. If they had to, you know, use a value x and then raise g to the power of x and they send us just g to the power of x, they prove to us that they actually did compute this value using in exactly that way and nothing else. So zero knowledge are very essential for MPC, and we would like to use zero knowledge. The problem is that zero knowledge might not be efficient, doesn't seem to be efficient. If the only proof methodology that we know is to reduce, you know, the problem we want, the statement we want to prove to an NP-complete statement, say about Hamiltonicity or satisfiability, and then generate a proof about it, then the size of the proof might be huge, okay? So people, like, for many years, thought that zero knowledge is, you know, it's a great theoretical idea, but it's not, you know, useful in practice. So today, this is the case, and in fact, in the next 2 days, we're going to see examples of very efficient new protocols for zero-knowledge proofs. Sigma protocols are a rather old example of quite efficient zero-knowledge proofs for specific problems. And maybe the first example of really efficient zero-knowledge proofs for problems which are useful. Okay, so Sigma protocols enable us to obtain efficient zero knowledge, and they're in particular good to prove arithmetic relations, in particular with regards to discrete log. Okay, and the best way to start with talking about Sigma protocols is with an example, and then we go to the definitions, so the general definitions. So this is Schnorr's protocol for proving knowledge of discrete log. So G is some group of order Q, and it has a generator, little g. And the prover and the verifier has some input h, and the prover knows the discrete log of h to the base g. So it knows w such that g to the w is equal to h. And the goal here is for the prover to prove that indeed it knows this discrete log without revealing anything else. Okay? So the prover proves to be that it knows the discrete log. So first I'll say what they do, then I'll show a diagram, then we prove properties. So the prover chooses a random R and sends A, which is G to the R, to the verifier. The verifier sends back to the prover a random string E of length T bits. And the prover sends back this value, and then the verifier does this check. So let's look here. So the prover has age and the discrete log of age. The verifier has age alone. The prover picks a random R and sends A, which is G to the R, to the verifier. The verifier returns a random string E of, say, T bits, say 40 bits. And the prover takes, okay, this R, this discrete log, plus E times the witness, the discrete log of age, sums them modulo Q, and sends to the verifier. And then the verifier does this check. It takes G to the Z and checks whether it's equal to A, the first message, times age to the E. Okay? So this is what they do, and we should show that this is, so first of all, it's very simple. Just send values, compute exponentiations. It's very simple. The question, what's happening there? So let's see. So first we want to see completeness, meaning that if P indeed knows discrete log, then it always succeeds in the proof. And this is easy. So G to the Z, okay, G to the Z, okay, this is Z. So it's G to the R plus EW, which is G to the R times GW to the power of E. G to the R is just A from the first message. And the second item is age to the power of E. And this is in exactly what is checked in this last step of the protocol. Okay? So the math works, and if the prover indeed knows discrete log, then it always manages to succeed to verify that this works. That it always manages to convince the verifier. Now, the prover also needs to prove that it knows the witness. And as we said, the prover should show, we should show an extractor showing how we can take this prover, use it as some kind of a black box, and somehow compute the witness. Okay? So we show that if a prover is able to convince us with good probability, then we are able to extract from this prover the discrete log. So we show this extractor. So this is the protocol. And the proof goes like this. This is not the proof that is run between the parties, but this is like a mental experiment we're doing in our minds, showing that if the prover is able to convince us, then it indeed knows the discrete log. So we say, okay, if the prover, okay, E is, this message E has, say, 40 bits. So it has 2 to the 40 possible values. So assume that P can answer 2 queries, any 2 queries, okay? If it can answer 1 query, then we don't claim anything. But if it can answer 2 queries, then we'll show that we can extract the discrete log from P. So if P can answer 2 queries, so let's say E and E prime, and suppose they can answer them successfully. So in the first round, P is sending A, and then there are 2 queries, E and E prime, that the prover can answer successfully, meaning that it can send 2 corresponding messages at the last round, Z and Z prime, that will convince the verifier. What does it mean for this message to convince the verifier? It means that they satisfy the equations. These equations of the last round. So G to the Z is equal to A times H to the E. And if the prover received the query E prime, he can send Z prime, so that G to the Z prime is equal to A times H to E prime. Now, if we do basic arithmetic and divide these 2 equations, we get that G to the power of Z minus Z prime equals to H to the power of E minus E prime. And if we divide, we see that H is G to the power of Z minus Z prime divided by E minus E prime. So essentially what we found here is the discrete log of H to the base of G. Okay? So basically, if the prover can answer these 2 queries at E and E prime, then given the prover's answers, we can compute a discrete log. So given this prover, we can extract the discrete log, basically compute a discrete log, and this convinces us that the prover has knowledge of the discrete log. So what it shows that, if the prover can answer a probability which is greater than 1 over 2 to the t, then it must know the discrete log. So if the prover can only answer one query, then we don't claim anything, but then it will only succeed the probability 1 over 2 to the t. If it can answer more than one queries, then we can extract the discrete log. Okay. Now what about zero knowledge? So we prove here first a weaker notion of honest verifier zero knowledge. We kind of say, okay, let's assume that the verifier is honest and it follows the protocol, meaning that it sends a random challenge E as it should. So this seems silly, like, the verifier, wants to learn more than it should, so it can send, like, any challenge, not necessarily a random challenge as the protocol tells it to send. But let's suppose, like, as the first step of our mental game, that the prover, that the verifier follows the protocol. And then we'll work with, probably tomorrow, with verifiers that do not satisfy the protocol, don't work according to the protocol. So this is the protocol. Okay. So, okay, we know that the verifier here sends a random message E, and we want to prove zero knowledge. What we want to do is that the verifier, giving only its input H, will be able to simulate the entire interaction between the verifier and the prover. So the verifier doesn't know the discrete log, yet it will be able to simulate this interaction, and this will convince us that the verifier doesn't learn anything from the interaction because it's able to simulate it. The way for the verifier to simulate the interaction is to compute these values, these three messages, not necessarily in the original step, A, E, and Z, but in a different order. It will first compute the last two messages, E and Z, and only then go and compute A. So what the verifier is doing, okay, it chooses random values for Z and E for the last two messages, and then it computes the value of A to be the one that will satisfy the last equation. So if it computes A as G to the Z times H to the minus E, then we see the last equation will hold, since that A times H to the E will give us exactly G to the Z as we need in the last equation. So does this give us the same distribution of the communication between the parties? So essentially, in the regular run of the protocol, we have messages A, E, and Z that are random, except for them satisfying this relation. So we have three messages, Z, A, and E, that are random, and have like one kind of linear requirement that it should satisfy. What we do in the original interaction, the parties choose A and E, and then there's only one Z that satisfies this requirement. Okay? What we do in the simulation, we pick E and Z, and then compute A based on these, based on the values of A and Z. So we just pick these values in different order, but we get values that have the same distribution. Okay? So we get exactly the same distribution. I mean, working in this different order is what enables the verifier to generate the simulation. So to actually prove to you that I know the discrete, so only the party who knows the discrete log can generate these values by taking A and E and then generating Z. But for the simulation, the verifier works in a different order. Starts from E and Z and then computes A backwards. So this is the simulation. It only works, though, if E is random. Okay. So this is not a very strong guarantee, because we assume here that the verifier picks a random E. But we can use it as a first step to achieve full zero knowledge, as I'll show tomorrow. And we should think, why is this is not a good proof simulation for any verifier, not necessarily a verifier that picks E at random. So what happens if the verifier picks E according to some algorithm? Why can't we pick E and Z and then go back to A? So think for a second. Yeah, exactly. So the problem might be that some strange verifier might see the first message A and then pick E as a function of A. Say apply a hash function, say SHA-256 to A, and this will be the message E, okay? This might not be a good strategy for the verifier, but it's going to kill our simulation. Because the way we do the simulation is we choose E and Z, and then we go back and choose A based on them. But if the verifier always chooses E as a function of A, it's likely that if we choose E and then then go back to A, we won't choose the E that corresponds to that A. Okay? So this is why the simulation doesn't work here. Okay. Okay. So after we saw this example, let's go to the general structure of Sigma protocols. So Sigma protocols have two parties, prover and verifier. They have a value X, and the prover have some witness W, that the two values are in a satisfier relation R. And the protocol always has three messages. The first message is some message A from the prover to the verifier. The second message is a random challenge E from the verifier to the prover. And the last message is an answer Z from the prover to the verifier. And then the verifier accepts based on the messages or the information it has. This is called the signal protocols. But if you look at the way the message go between the parties and maybe make the lines a bit slanted, then you might see here the letter sigma. I mean, one line is still missing, but I think that this is the source for the name sigma protocols. So these are very simple protocols. Only three messages, and apparently they're good for many examples. And for many years, they were, I think, the main main efficient zero knowledge tool that we had. Okay, and okay, we got about definitions. So completeness should be as in ZK. If X is in the language, then the prover should always be able to prove that X is in the language. Special soundness, meaning that there's an efficient extractor algorithm that giving any X and two transcripts which start from the same first message A and then have two different challenges from the verifier, one E and one E prime, then the extractor is able to extract the witness. Okay, again, if the prover is able to answer two challenges for the same initial message A, then there is an extractor that is able to extract the witness from the answers of the prover. Okay, this is exactly what we showed for the discrete log. And then the special honest verifier zero knowledge property, meaning that there is an efficient simulator that giving any input X and challenge E is able to output a transcript of messages which has exactly the same distribution as in the real one. Now, if the verifier is indeed choosing E randomly, then this will have exactly the same distribution as in the real one, because the simulator will choose X randomly. Actually, any method of the verifier to choose E that does not depend on the initial message A will work here. So if somehow the verifier chooses E as a function of X, I think that everything should work here as well. The simulation will work. The problem is if the verifier chooses E as a function of the first message A. Okay, another example, signal protocol for proving that a tuple is a Diffie-Hellman tuple. Okay, so what is a Diffie-Hellman tuple? It's four items, G to the power of A, G to the power of B, and G to the power of AB. Or in other words, these are four values, okay, such that four values, the discrete log of the third value to the base of U to the base G is a discrete log of V to the base H. Okay, so U is G to the W and V is also H to the W. So basically, two pairs of values that have the same discrete log. Okay, so this is a Diffie-Hellman tuple. And it's used in many protocols. It's related to Diffie-Hellman key exchange, El-Gamal encryption, and so on. Okay? So what we're going to do here is prove that this tuple is indeed a Diffie-Hellman tuple. Okay? So this is not by itself a proof of knowledge. We don't want to prove knowledge of the discrete log. We want to prove essentially that the two discrete logs of these two pairs of values are the same, are both the same. Okay? But the way we're going to do the proof is going to be a proof. We're also going to show that we know the discrete log. Okay. So the protocol is very similar to, let's go back, is very similar to the proof of knowledge of discrete log. So in the proof of knowledge of discrete log, the prover sends a single value g to the r, a which is g to the r. Here it's going to send two values, a which is g to the r and b which is h to the r. It gets back a random e and send back the same z as it sends in the regular proof of knowledge of or discrete log. So this is the protocol. So it's like the proof. So it's essentially the protocol for, okay, if we just take this A, E, and Z, that's the protocol for proving this knowledge of the discrete log to the base G. And if we take B, E, and Z, it's the protocol for proving this knowledge of discrete log to the base H. So basically, we take two protocols for knowledge of discrete log and do them together, okay, with the same challenge. Okay, so complete this work just as like in discrete log protocols. What about special soundness? So without going into the actual arithmetic which is done there, so if we take A, E, and Z, we showed 5 minutes ago that based on them we can compute the discrete log of U to the base G. And if we take B, E, and Z, we know that they, if we get two successful interactions, we can use them to compute the discrete log of W to the base H. So if we take another look, this red mat over there, we can see that both of these discrete logs are going to be the same. Okay? So basically, if you do the math, you see that you can compute both discrete logs, and you're going to use the same equations, and you get the same values, so discrete logs are the same. So essentially what we did here, instead, in addition to proving that the two discrete logs are the same, meaning this is a Diffie-Hellman tuple, we also proved here that we know the discrete log. Okay, this is like another feature that we get. Okay, special honest verifier zero knowledge. It's exactly like in the discrete log proof. So this is another example now. I don't have it in the slides, but what if I want to prove that an El-Gamal encryption is an encryption of some value? Okay, so I don't have it in the slides, but those who are familiar with it, El-Gamal encryption is basically a Diffie-Hellman tuple where the last value is multiplied by the plaintext that I want to encrypt. So if I want to prove that this is an encryption of 2, then if I take the last value of the encryption, last component divided by 2, basically I should get a Diffie-Hellman tuple. Okay, so what I can do there is, if I know how to prove knowledge of discrete of Diffie-Hellman tuples, I can also prove knowledge of the plaintext encrypted in encryptions. Okay, and you can do many other things by being able to prove relations about discrete log and about Diffie-Hellman tuples. Okay. So some basic properties. Any sigma protocol is interactive proof with soundness 2 to the minus t. You can compose sigma protocols in parallel and still preserve all the properties they have. And any sigma protocol is also a proof of knowledge in the sense that Yehuda defined yesterday. With error of 2 to the minus t. Now, 2 to the minus epsilon, 2 to the minus t. Now, this proof requires some work, and we won't go into details here because it does require some work. Okay. Okay. So we got here sigma protocols which are, very efficient. Honest verifier, unfortunately. Zero knowledge, 3-1 protocol. 3-1 is great. Honest verifier is not great. And they can apply it to many problems. I think essentially all discrete log or Diffie-Hellman based statements, encryption, so on. Knowledge that commitments are to a specific value if the commitment is based on discrete log. Proving that the parallel encryption is encryption of 0, all kinds of about RSA encryptions. They're very useful to prove properties about public key encryption. So they're great. They are interactive because they need to do 3 rounds. However, it's easy to convert into a non-interactive version using the Fiat-Shamir paradigm. So the Fiat-Shamir paradigm converts non-interactive protocols to converts interactive protocols to non-interactive ones. And here, since we only have 3 rounds, the conversion is the simplest that can be. So what the parties do, the prover generates A, and then instead of waiting to receive the challenge E from the verifier, computes the challenge as a hash function of the initial message A and of X. Then based off this challenge, it computes Z, and then sends these 3 values to the verifier that verifies them. So one thing to keep in mind here, as if we use the Fiat-Shamir paradigm, the challenge should be long. Okay? So suppose that we want the proof to hold with probability 1 over a million. If we have an interactive proof, then we can be happy with the challenge, with the verifier sending a challenge of length, say 20 bits, because 2 to the 20 is a million, and the probability of the approver who doesn't know the witness to prove is only if the prover is able to guess what challenge it will receive from the verifier, so it's 1 over a million. So this is for the interactive protocol. What happens if we want to use the non-interactive version using the Fiat-Shamir heuristic? Can in this case as well, we can use a challenge here, which is 20 bits. So age will be a function which takes the first message X and computes a 20-bit output, and this will be the challenge. Would that be good for our proof? It will not. Okay, why? How can the prover cheat here? Okay, so this is a non-interactive protocol, and suppose that we say that E, the output of age, is only 20 bits long, and you want to prove something, and you don't know how to prove it. You don't have the witness, and you want to cheat. Okay, how can you cheat here? The birthday paradox? No, not necessarily. Okay, recall that even if you don't know the witness, okay, still there is one challenge E on which you can cheat in Sigma protocols. Okay, let's go back to the zero knowledge proof. Okay, let's think about the proof of this being zero knowledge. How did we do the proof of zero knowledge? The prover, picked a random E, picked a Z, and then picked the A that will satisfy, the relation with this, with E and Z. Now, if the prover is able to somehow guess in advance, what E is going to receive, then it can send the right A that will, satisfy everything. Now, in an interactive protocol, when I interact with you, and the space of challenges E has 20 bits, so it has 1 million items in it, the probability of me guessing exactly what challenge you're going to send me is 1 over a million, which is not good. Now, suppose now I'm working in this Fiat-Shamir paradigm, okay? So I choose an A, and then I compute E as a hash of A and X, and then I should compute a Z. How can I cheat here? So suppose E is only 20 bits long, okay? So what I say, okay, I'll choose E, I'll choose Z, and based on them in the simulation, I can know, what A will be, will make me finish this proof successfully. Now, this will only work here if the hash of A and X is equal to the E that I chose here, okay? What's the probability of this? 2 to the power of minus, the length of E. If E is only 20 bits long, then this, I'll be successful probability 1 over a million, okay, which is not that bad. So I'll try 1 million times, and then I'll be able, to find, I'll pick an E, pick a Z, get A, and probability 1 over a million, the A will, be good for me to, to compute this, this proof. And the thing here that here I can, if I do this non-interactive proof, I can do this test, offline, at my spare time until I find a successful proof. So if I want to do these non-interactive proofs, we will need the length of E to be long so that the prover cannot go over, cannot do, cover the entire space of possible values to E, or in order to find a successful successful proof. So suppose that E could be 128 bits long, or maybe 80 bits, and that should prove be good. Okay. One nice thing here is that here we don't have to care anymore about honest verifiers. Okay. So in regular Sigma protocols, we need the verifier to choose E at random. Here E is chosen by the random hash function. So the prover is choosing E by itself, so it doesn't have to care about the verifier being honest or not, because the prover is doing everything. So that's great. The thing which is not great is that this proof only works in the random oracle model. Okay, so the prover assumes. Okay, so we don't like the random oracle model because that's the result of Canetti, Halevi, and Goldach showing that for any protocol in the random oracle model, it cannot be instantiated in the real world, and so on. So the proof is heuristic and not. And not in the standard model. Still, these protocols are very efficient. Okay. So Sigma protocols are very useful because we can apply different tools to them that are useful for different tasks. So I'll discuss 3 tools, the first one today and the next other 2 tomorrow. So the first one is about using Sigma protocols for proving compound statements, like the end of a few statements or the O of a few statements. And then I'll talk about doing zero knowledge from Sigma protocols. So first about compound statements. So suppose I want to prove the end of multiple statements, meaning I want to prove that all of them are correct. And for each statement, I have a Sigma protocol. Then I can run all these Sigma protocols in parallel. So in the first one, I'm going to send the first message for all of these statements. In the second one, I'm going to get an E for all of these statements, and I'm going to send the answers. And actually, the challenge E can be the same E for all of these statements, for all of these proofs. Okay? So I can do multiple proofs in parallel. Sometimes I can do it better. Sometimes I can batch a few proofs together, like proving many, knowledge of many discrete logs can be batched together using fewer messages than the number of discrete logs I want to prove, but I won't go into detail. Also here, I can prove in parallel multiple statements of different form. So one could be knowledge of a discrete log, the other could be knowledge of Diffie-Hellman tuple, the third one could be something about RSA. I can do all of them in parallel. Okay, so end is a bit simple. The O is the nice thing. So giving 2 statements, I can prove that I know a witness to either the first one or the second one. So for instance, if I have 2 values, I can prove to you that I know the discrete log of either the first one or the second one, and I'm not going to reveal to you which is the discrete log that I know. Okay? So this is very useful. I can show you 2 values, tell you, I know the commitment or the encryption or the plaintext in one of these values, but I'm not going to show you which one it is. So this is something like really cool and really useful. So let's see how it goes. So it's a bit more complicated, and the solution is a paper by Kramer, Damgard, and Schumacher, which is based on a very nice idea. So I want to prove that I know one of 2 statements. For one of them, I know the witness, so I can prove it. For the other ones, I don't know the witness, so I must cheat in the proof. Okay? Now, how can I cheat? So the simulator, the zero-knowledge simulator, is essentially a way of cheating. What was the simulator? How did I generate the distribution? I chose the challenge E, then the last message, then based on them, I generated the first message. So this zero-knowledge simulator, essentially what it tells us that if the prover knows in advance what will be the challenge E that is going to be sent in the second step, then it can send a message in the first step that will, satisfy everything. Of course, if I know what is, challenge I'm going to get, then I can prepare and answer that challenge. So the idea here is to design a protocol where in one of the two proofs, the prover will know in advance what challenge it's going to get. In the second proof, it's not going to know in advance, but there it actually knows the witness, so it can prove anything it wants. It can prove anything and answer any challenge. Okay? And the verifier will not know which proof is which. So here's the protocol. So we want to prove either x0 or x1, and there are two witnesses. So the prover sends two first messages, A0 and A1. First, I'll go over the protocol quickly, then I'll go in detail. And the verifier sends a single challenge E. And then the prover replies with two challenges. The first challenge, E0, would correspond to the first message, A0. The second challenge, E1, correspond to the second message. And the two challenges, the prover picks them. So we let the prover pick the challenges, but they must satisfy that the XOR of the two challenges should be equal to E, the value that was sent from the verifier. So basically, the verifier sends some constraint on the two challenges that the prover can use, and tells the prover, pick any challenges you want, but they should satisfy this constraint that the XOR is equal to E. And then the prover continues with the last messages, Z0 and Z1, that work with these challenges. And V accepts if two conditions hold. One is that the XOR of E0 and E1 is indeed equal to E, and also that these two proofs, the first one and the second one, are correct. Okay, so how does it work? So the prover sends the first two messages. So suppose for now that the prover has a witness for x0. It knows the discrete log of x0, but doesn't have a witness for x1. So for the first statement, he can prove it. The second one, he has to cheat. So it already prepares the way it's going to cheat for the second statement. So basically, it chooses in advance the challenge E1 that it's going to answer. Then it runs the simulator and knows, okay, for this challenge, if I get it, if I send this message A1, then I get the challenge E1, then I'm going to send Z1. This is going to satisfy the proof. So it prepares, how it's going to cheat. And then it sends to the verifier A0 and A1. A0 is just random, and A1 is the one it prepared for this cheating. And the verifier sends to the prover this challenge E, and the prover works like this. Okay, E1, it has to choose E1 that it prepared in advance. And then for E0, it computes E0 as the XOR of E that is received from the verifier, and E1 it prepares in advance, so it gets a certain value for E0. And then it continues with Z0 that finishes the proof with E0 and Z1. So with E0, this is for the proof of X0. So for X0, the prover knows the witness, so it doesn't care what E0 is. It can always complete the proof. And for the first state, for statement 1, it already prepared the simulation for E1, so it knows how to complete the interaction. And then the verifier verifies that everything's okay. So why does this convince us? So first, if about completeness, then I just showed how the prover can cheat here, if it knows, not cheat. I just showed how the prover who knows one of these statements can prove that it knows one of these statements by proving one of the statements and cheating in the other one. Okay, so this is what I showed. What about soundness? We want to show that the prover that doesn't know at least one of these statements cannot complete the proof. Okay, so first let's look at the intuition, then a better draft of a proof. So if the prover doesn't know a witness for X1, it can only answer for a single challenge E1. And this means that for X0, the challenge E will define a random challenge And this means that for E0, the prover will only be able to prove if it knows an actual witness for the first statement, for statement 0. Like, doing it more accurately, so, okay, this prover sent the first message A0 and A1. Now, suppose it can answer two different challenges, E and E prime. Now, it can choose for each challenge, it can choose, E0 and E1 for the first challenge E, and E0 prime and E1 prime for the challenge E prime. Since E is different than E prime, then in one of these pairs, either E0 is different than E prime, or E1 is different than, either E0 is different than E0 prime, or E1 is different than E1 prime. Okay? So therefore, for at least one of these two statements, the prover will have to answer two different challenges. Now, it can answer two different challenges only if it indeed has a witness to that statement, meaning that it actually knows a proof for that statement. Okay? So this convinces that it knows a proof for at least one of these two statements. And about the zero knowledge property, we just do simulation as the simple case. And as a note, nothing in this proof required that the two statements are for the same, of the same type. So the first statement could be that I know the discrete log, and the second statement could be that I know like a Diffie-Hellman tuple, and I can prove to you that either I know this discrete log, or I know, or the second, tuple is a Diffie-Hellman tuple, and I can prove all of like statements of different types. It works well. Okay, and what we did here is to prove like one out of two. The prover proved that it knows, one of these two statements, and the next step is to prove k out of n statements. Okay, so there are n statements, and the prover would like to prove that it knows at least k of them. It can prove at least k of them. So say we have 10 values, and I want to prove to you that I know discrete log of at least 4 of them. And the way to do it is very similar to how we do secret sharing using polynomials. So it's not necessarily by doing secret sharing, but we're using polynomials or linear constraints in exactly the same way. So let F be a field, and let's look at some basic facts from algebra. So if we have D plus 1 pairs, so a pair is like AY, BY, BAI, BI, so D plus 1 pairs of points define a unique polynomial P of degree D that goes through them. Okay? So over D plus 1 points, there's exactly one polynomial of degree D. Okay? This is basic fact from algebra. And we know that this polynomial can be found efficiently using interpolation. So that's great. And another thing is, once we get this polynomial, okay, if the points that we use to interpolate this polynomial were random, okay, so once we get the polynomial, we don't know which points were used to interpolate it, okay? So the polynomial is, x squared plus 2 times x minus 5, okay? And you know that I used like 3 points to interpolate it. You don't know which points I used to interpolate it. If you know that my data is random, I can use arbitrary points, and the polynomial doesn't leak to you which points these were. And this is something we're going to use here. Okay, so we want to prove a signal protocol for k out of n statements. So there are two types of statements. Statements for which the prover knows the witness and can complete the proof, and statements for which the prover doesn't know a witness. So A is the indices for which the prover knows a witness, and the size of A is k. And B is the indices of statements for which the prover doesn't have a proof, doesn't have a witness. Okay? And we're going to use a polynomial with n minus k plus 1 degrees of freedom. So degrees of freedom is the number of indices in which the prover has to cheat plus 1. Okay, so this is a polynomial of degree n minus k. And the polynomial is going to be defined for x values of 1, 2, up to n. Okay, so the first step, for every index I for which the prover doesn't know a witness, so it needs to cheat, it uses the simulator to basically generate the messages AI, EI, ZI that it wants to see in the interaction. So for these indices in B, it must cheat, so it prepares in advance what it's going to send in the protocol for these indices. And for the other indices in A, it can, it knows the witness, it can prove, like a normal way. So it just generates the messages A as the protocol tells it to generate them. And then it sends all the A's to the verifier. So for the good indices, the A's were chosen by the protocol. For the indices in the set B, where the prover needs to cheat, it prepared a simulation and sends the A that it had in that simulation. Now, this is what it sent to the verifier. And then the verifier sends the prover a single field element, E. And then the prover finds the only polynomial of degree n minus k that goes through the following points. So the point 0 and E, x is equal to 0, y is equal to E, where E is the value it received here from the verifier. And then the points I, EI, for all the values for which it had to cheat, for all the values that it doesn't know how to prove. Okay, so let's see why it's interesting in a second. And then what the prover is doing, okay, for each of the indices 1 to n, it takes this polynomial, compute the polynomial at that index. So f of 1 is E01. This is going to be the challenge it's going to use for the first statement. F of 2 is going to be E2, the challenge used in the second statement, and so on. So it gets n challenges and uses them, and then answers them with the third messages Z1 up to Zn, and sends everything to the verifier. And then the verifier is doing two things. It first verifies that all the EI values it received from the prover are on a polynomial of degree n minus k. And it checks that each interaction works properly. Okay. Let's look at it again. Okay. So basically, what happens here, okay, so the prover, okay, already had like n minus k constraints on the polynomial, because in n minus k interactions, it had to use a specific value for the challenge, okay? And then it also received this challenge E from the verifier, and the polynomial at 0 must be equal to E, so this is like another constraint of the polynomial. Together it had n minus k plus 1 constraints on the polynomial, which define a single polynomial that goes through of degree n minus k. Okay, so let's look about properties. Okay, so suppose that the prover can prove less than k statements. In this case, we would like to say that the prover cannot complete the proof. Okay, so the prover proves that it can prove k statements. We want to show that it doesn't know how to prove k statements, then it fails. Okay, so if it knows less than k statements, then for more than n minus k statements, it must cheat. Okay, so for more than n minus k statements, it needs to generate a simulation, and there's a single challenge it can answer for all of these statements. So these n minus k statements, so these more than n minus k statements define a polynomial of degree n minus k or more. Okay, we have more than n minus k constraints. They define a polynomial of degree n minus k or more than that. And essentially, the polynomial that the prover has to send to the verifier in the proof must be of degree n minus k. But these, places where it has to cheat already define this polynomial. And then in the second step of the proof, it gets the challenge E from the verifier, and the polynomial must satisfy that the polynomial at 0, f of 0, is equal to E. But the polynomial is already defined by the location in which the prover has to cheat. Therefore, the probability of the polynomial at 0 being equal to the challenge it receives from the verifier is 1 over the size of the field. So the success probability of the cheating prover here is 1 over the size of the field, which is not very good. Okay, so here if we can, I showed how to prove AND and how to prove OR. So together we can generate any monotone formula. So by using these constructions, I can prove any monotone formula of statements about things I want to prove. And this is in general extremely useful. I think in the earlier day, in the previous lectures, you saw claims that I have to prove that either I know this thing or I know that thing. So this is the way how to prove this thing. And this is, as I said, based on a paper of Kramer, Damgard, and Schumacher's from '94. A really nice paper. So I think that this is all for today, and tomorrow morning we'll continue with how to build full zero knowledge from Sigma protocols. Thanks.